All right, okay, so we're going to start with logarithms. That's going to be the first unit that we're going to look at, logs and exponentials. So logarithms are something that you should have done in Math 3 and that we're going to look at together here. So first thing I want us to understand is what is a logarithm? What in the world does it mean? Because I feel like it's something we learn a lot of times and don't really know what it represents. It's just like a series of rules that we have learned. So a logarithm is the power to which a number must be raised in order to get some other number. Okay? So, for example, here I've got one that hopefully we can do without a calculator. 2 to the x power equals 16. What should that x be there? X should be 4. 2 to the 4th power is going to give us 16. All right? So, what we have just done there, although it's a really simple basic thing, is we have taken a logarithm to solve that. Really, we're just like thinking 2 to what? To power, right? So this would be called the base 2 logarithm of 16 is 4. The way that is written in math would be like this. Log base 2 of 16, right? So that base 2 logarithm of 16 is 4. What it means is 2 to some power has to equal 16. So when you see log base 2 of 16, you may not immediately think 2 to some power equals 16, but that is what it means. Okay? So another example is not quite as easy to do in your head. You've got 2 to the x power equals 1024. So, what would I have there? You can grab your calculator and guess and check till you find something. 10? I think it is 10. Check me there. See if 2 to the 10th power is 1024. I think it is 10. Is that right? And you guys also may have used the TI-84 calculators to varying degrees. So let me know. We're going to use them some. We will also still use Desmos some because I'm not sure what you're going to run into in college. The problem with Desmos is letting you have Desmos lets you have the whole internet most of the time, unless it's built into your testing platform. So I'm not sure what you're going to run into in college. I think there are still a lot of college professors that require you to use a TI-84. So we're going to try to use it some just so you're familiar with it a little bit. Desmos is better. I like Desmos better for a lot of things, but I'm going to try to use both some. So this is 10. So this would be the base 2 logarithm of 1024 is 10. So that's written this way, log base 2 of 10. I'm sorry, of 1024 equals 10. So when we see logs, we need to think about exponentials, right? They go hand in hand. In fact, I usually teach logs a little bit different than Coach Wood has taught you, usually, or Mr. Brown. And I like to think of these as inverses because they are inverses of each other. Logs are inverses of exponentials. Although everything you have learned about logs and exponentials so far does still work the other way, so you don't have to necessarily think of it the way. I'll show you both ways. I'm getting ahead of myself. So. All right, so just to look at some applications. I wish we had more time to look at applications in pre-cal. You'll find that a lot of the stuff we do in pre-cal is very, we're looking at how to do the algebra, and we don't look at the applications as much because we have a lot of things that we need to cover. And the main point of this class is to make sure that you have all the tools that you need to be successful in calculus. So it's making sure you understand the upper level algebra and trig that you will need to use in calculus. So a lot of times that does end up just being the algebra and manipulating equations and not so much the applications. So I'll try to pull those out some. I would like to spend more time with them, but the our main focus is getting those tools for calculus. So, several things that use logarithms. Lots of things are going to be on a logarithmic scale. The Richter scale, which is your earthquake intensity, is used. As I was looking this up, I found it very interesting. We actually do not use the Richter scale anymore. We refer to it like the Richter scale. Whenever they tell you that an earthquake is a 7.2, you're thinking Richter scale, but technically they are not actually using the Richter scale. There is an updated scale for that. The Richter scale was kind of like the original for that. They have changed it, and so scientists, at least, now I don't know what the news people are telling you. They might have Richter numbers, but scientists are going to use the moment magnitude scale, which is our modern earthquake intensity. So it's very similar to the Richter scale, but a 7 on the Richter scale is not a 7 on our today's moment magnitude scale. So if you're looking at old earthquakes, sometimes there are differences because of that. That's just a little tidbit of information I found whenever I was looking at this. Your decibel scale, which measures sound intensity, is going to be on a logarithmic scale. So we'll look at a chart for that in a second. It's used a lot in data analysis when you have really large numbers that you have to deal with. For example, with COVID numbers, a lot of times they would look at a logarithmic scale graph for that, because we started tracking COVID numbers when we had like 5 cases, but of course that skyrocketed. So a lot of times you look at a logarithmic scale for that. And it basically any other time that you're dealing with very large numbers, sometimes those logarithms can be helpful. So here is an example of the Richter scale. And so what's important to remember here is that when you're looking at logarithmic scales, each level is a certain magnitude higher than the next. So, for example, if we have a 3 to a 3.9, it's felt by many people, but there is no damage. So it's very minor. You know, we've had earthquakes here. You may have remembered there was one in Sparta. It was actually higher, but by the time it was here, we weren't feeling I think it was almost a 5. But you know, we could feel it here if you were paying attention. If you weren't, you might not. But whenever you go from one to the next, it's on a logarithmic scale with a base 10, so it's 10 times worse. So going from a 3 to a 4 is 10 times worse. So if we go from a 4 to a 5, it's 10 times worse again. Well, if you multiply something by 10 and then you multiply it by 10 again, that means that a 3 to a 5 is 100 times worse, right? So when you're looking at the difference between a 6 and a 7, it's big, right? And then between a 7 and an 8, big, right? And then like a 3 and an 8, you can't even really compare, right? If you've experienced a level 3 earthquake and you tell somebody that just went through a 7, that you also experienced an earthquake and you know how they feel, they're going to think you're crazy because the ground just shook a little bit for you and their house fell down, right? So it's used this way because there is such varying intensity, right? So it's important to remember that whenever you hear things about earthquakes, because it's really easy to think that a 8 is really not that much worse than a 7, but an 8 is a lot worse than a 7. Noises also do this. I have turned on the feature on my phone or on my watch where it will tell me if I'm in an environment that is too loud. I turned it on because my husband wants to play the electric guitar in my house at very high levels. He's going to be deaf by the time he's 60. And so I turned it on to try to prove to him that he was playing the guitar too loud. And it did set it off. It told me that I was in a loud environment. And then I've just left it on. So like this weekend, I was at a birthday party at the Fairfield Inn in the pool with like a bunch of 6-year-olds running around screaming. It was terrible. It went off really quickly then. But your decibel levels, now these do go up by 10, but you're adding 10 each time. And that's not what's happening in intensity. Your intensity is multiplying by 10. So whenever you're talking about 30, leaves rustling, soft music, whisper, this is really low. But whenever you get up here, you know, a 90, I think my watch goes off at 90 maybe. Or maybe it's 85. I can't. 85 is when they become harmful, but I think my watch goes off at 90. So that's 1, 2, 3, 4. Oh, wait, this one's weird. I don't like this chart because it skips 50. So 30, 40, 50, 60, 70, 80, 90. We're talking 6, but that's not 6 times worse. It doesn't mean that sound is 6 times worse. It means it's 1 with 6 zeros times worse, right? So going from this up to your 90 right here, it's 1, 2, 3, 4, 5, 6. It is a million times worse, right? So leaves rustling, soft music is never going to damage your hearing. No longer, if you listen to it all day, every day, you know, it's not going to damage your hearing. But at 90, which is a million times worse, if you are listening to something like this over time, it can damage your hearing. You know, once or twice, not a big deal. One birthday party at the Fairfield Inn is not going to cause you to be deaf whenever you get old, but if you had to go to one every day, you would become insane way quicker than you would become deaf, but you would eventually also be deaf. So these are some examples where these apply. So let's just go from the very basic, rewriting log and exponential equations. So if I have, I'm going to call this b to the a equals x. So if I have an exponential, it can be written with b as my base. So log b here is the base. So I use the letter b specifically because we call this the base for our exponent, and we also call this the base of our logarithm, right? So this b becomes this b over here, and it would be log base b of x equals a. So a lot of students, usually when they get to me, they have learned how to rewrite these just by basically using, you know, this pattern that you're seeing. That base becomes the base on the logarithm. Then the a right here is going to go to the other side where it's equal to, and the x comes over here. Generally, you're trying to break up that a and b, so you don't want b and a to be right here. So for a problem that would look like this, log base 5 of 25 would equal 2. Okay, I want to propose to you a different way of thinking about this. Now, this works, this is fine. If you got this down, you like it, you know, I mean, it's fine. I want to propose to you, really it doesn't do anything much different as far as your answer in the end, but I think it does make a difference as far as your understanding. So logs and exponentials are inverses of each other. They undo each other. So if I have 5 squared equals 25, let me propose a different way of thinking of this. So if I want, it's particularly helpful like on number 6 where I have an x. I know what variable I want. But if I want to break these up, if I want to write this as a log, to get rid of my base over here, I could do a log base 5 of this side. And then I could also do a log base 5 of the other side as well. Because our principles of solving equations tell us if we do something to one side, we also have to do it to the other side, right? So if I do this, if I have log with a base 5 and I have 5 to the second power, these cancel each other out and I'm just left with the 2. And then on the other side, I have log base 5 of 25. Okay, see, this is the same thing that I get over here, except for my sides are reversed, but that doesn't really matter, does it, right? It's still equivalent there. So, as another way to think about this, particularly if you get your formulas mixed up, I think this is easier to remember, but it's up to you. So, like if I do that again for the next problem, if I have 8 to the third power equals 5, 12. If I want to get rid of that 8 right there, it's 8 raised to a power, so I can get rid of it by doing a log base 8. And I can do that on both sides. And you are taking log base 8 of each side. So like if I wrote it out neater, it's log base 8 of 8 to the third power equals log base 8 of 512. And then so when you do, as long as the bases are the same, if you have log base 8 of 8 raised to a power, these 8's right here cancel. You're just left with a 3. And then over here you would have log base 8 of 512. Okay, or you can just say, oh, 8 is going to be my base, so log base 8. I got to put 512 with it, and then it will equal what's left over here is 3. If we look at that third one, I've not given myself enough room. I'm going to put it over here. If I've got 6 to the x equals 125 here, if I want, particularly in this, we're going to see this a lot when we're solving equations, is where you're trying to find that x. So you got to get rid of the 6. The 6 is a base for an exponent. You can't just like divide by 6. So you're going to do log base 6 of this side and log base 6 of this side. And then log with the base 6 is going to cancel with the 6 here. And so we'll get x just left on that side. And nothing cancels over here because you don't have the same thing. So it's log base 6 of 125. Okay, it's the same as rewriting that you have done before. It's just a little bit different way of thinking of it. There. It also works the other way. So if I've got, for number 4 here, I've got log base 5 of 625 equals 4. The opposite of a logarithm is exponential. So if my base is 5 right here, I could do 5 raised to this power right here and 5 raised to this power right here. Now I'm going to write it out this time. What I'm doing there, I've got 5 raised to the log base 5 of 625. I wouldn't usually write this out, but just to be really clear what's happening. And then I've got 5 to the 4th power over here. So if I do 5 to that power on both sides, that 5 and the log base 5 are going to cancel out. Because when we have a power, a base raised to a log with that same base, those cancel each other out. So we get 625 equals 5 to the 4th power. Now, if you're like, Miss Hyatt, it seems crazy. Why are you doing that? I like it the way that I learned it. It's fine. Like, I don't have to do that every time. Here, my base is 2. I can do 2 to the 3rd power, right, equals 8. You can do it that way. Or, to get rid of a log with a base 2, you do 2 to the power, 2 to the power, right here. These cancel. 8 equals 2 to the 3rd power. It's just going to be which side of the equal sign your information is on is the only thing that switches there. We okay there? Questions? Does that make sense? Okay, so like if I think about it with inverses here, log base 7, the inverse of log base 7 is 7 to that power. 7 to that power. So that 7 right there will cancel with your log base 7, and you'll get x equals 7 to the 10th power, which I'm going to leave 7 to the 10th power because that's going to be a huge, huge number when you multiply 7 10 times. So we'll just leave it like that. Okay, so some things I'm going to give you, just going to ask you to rewrite. But the main reason I want you to do this is because it's a tool for solving equations that we need to know. So, there are some special logarithms that we need to know about. If you ever see log written without a base, it is assumed that that base is 10. And that is called the common log. Okay, so its special name is the common log, but a lot of times we just call it log. All right, it is the one that we're going to see it used a lot, particularly like with the Richter scale and decibel scale, you would have a base 10, right? We usually look at things in magnitudes of 10 because we have a base 10 system. The other one you're going to see is natural log, and it's going to be ln of x. We don't ever write it like this right here. Like if you write log base e of x, it makes it look like you don't know what you're doing because you should just call it natural log of x. But as far as understanding it goes, it is log with a base of e. Okay, you should have seen e before. E is Euler's number, and it is like 2.178. Is that right? Let's go to our calculator here. E to the first power is, oh, sorry, I'm using the 89, 2.17828. And if we get time, we'll talk about what Euler's number is and where it comes from. But it's like pi. So when you see E, it is actually a number. It's 2.17828, and that goes on. It doesn't end there. So when you see E, that is this number here, and it's a really important number that shows up in a lot of different places that are kind of cool, and we'll talk more about that. We call this our natural log. Have you guys seen both of those before? I mean, I'm not asking if you remember every detail of it, but you've seen E before, and you've seen natural log, you've seen log without a base written. Getting nods, so that's good. All right. So logarithmic and exponential functions are inverses of each other, which is what I was talking about earlier. Whenever we have a function that is log base log base 10 of x, the inverse of that would be 10 to the x power. What this means here is that you are not, for your domain, you are not going to be able to take the log of any number less than or equal to 0. Let's talk about why that is the case. If I have log of x equals, let's talk about why we can't have negative numbers first. So if I have log of -1 equals, I'm going to put the x here. I don't know what it equals, right? This log does not have a base written. So, Abby, what is the base if it's not written? 10. Very good. All right, so if I want to get rid of that log base 10, the base is 10. I could do 10 to that power on both sides, or I could just rewrite it. Either way. 10 raised to log base 10. That cancels out. I just have my -1 equals 10 to the x power. Can we raise 10 to any power that will give us a negative number? You can't. What's going to happen if I do like 10 to the -1? Does anybody remember what to do with negative exponents? Negative exponents, like if I type that into my calculator, 10 to the -1 I get 0.1. So it's not negative. It doesn't give me a negative number. Negative exponents. I teach my Math 1 kids, they're like bad children, and what should you do with bad children? You should lock them in the basement. So you move them to the other side of and that makes their exponent negative. So negative exponents don't give you negative numbers, they give you fractions, right? They're still positive, but they're fractions. So there's nothing here that could give you no number exists that would give you a negative 1 right here. So that's why we cannot take the log of any number less than or equal to 0. The same would be true for 0 here. I can't ever get that to equal 0. 10 to any power is still going to have some sort of positive value. It's never going to equal 0. It might be really close to 0, but it's not going to equal 0. So that's important to remember for our domain. And then there's one more thing you need to know, particularly, mostly for us using the TI-84 calculator. And if you have a new fancy TI-84 calculator, yours might be able to do a base on a logarithm. If you are using the ones here that are not new and fancy, then you're going to need to know this, and there could just be times where it's important to know. If I have log base 7 of 8, and I need to type that into this calculator, the way that I'm going to do that is log 8 divided by log 7. Now, again, if you have the fancy new calculators, which it looks like most of you are using mine today, if you have the fancy ones, I think when you hit log, it lets you put a base in, but these do not. So log, and actually a couple of you might have like newer calculators that look the same as everybody else's. Those might even do this here, but I have some of the oldest calculators in school, so probably. So make sure you close that first parentheses right there for your 8, because if you don't, you'll get the wrong answer. So you got to do log of 8 divided by log of 7. Desmos, we'll do these. We'll let you type in the, if you're doing it in Desmos, because a lot of you will probably need that for homework. Desmos, if you go to functions, you can go to log, and you have options. LN and LOG you can just type in. That's what I usually do. But if you want a base that's different, you do log with that base, and then you could type it in 7, 8. Okay. Yeah, you can do that if you would like. So log base 7 of 8. Here you can type it in this way, or honestly, I still do this. I still just do it this way, because I think it is easier to do than, because you can type it in without having to use the function menu. So I still do it that way in Desmos. Either one will work. But if you're using the TI-84 calculator, and there might be some things where I don't let you have Desmos, I only let you have the calculator because Desmos is like too powerful for what we're doing. So you might need to know that there. All right, so let's solve some equations here. On the first couple, I'm going to look at these, both ways. But in general, I like to use that inverse mentality, like I'm doing the opposite of the function here to solve these. So that's what I think of. I'll show you how it works both ways. So for this problem, the way I like to think of it is 5 is my base, and I'm raising it to the x power. I cannot just divide by 5, right? Because then x is an exponent, but how do I know it's an exponent if it's not there, right? This is not 5 times x. If it was 5 times x, I would just divide both sides by 5. It is 5 to the x power. So to undo an exponential, you have to use a log. So what I would do is I would do log base 5 on this left-hand side and log base 5 on that right-hand side. Oops. So when you're doing log base 5 of 5 to a power, that cancels. You just have x over here. And then you got log base 5 of 9 over here. And you can just type that into the calculator. Log of 9 divided by log of 5 will give you 1.365. I realize some of you guys are seniors, so you're definitely not taking AP Calculus with me next year, because hopefully you are going to graduate at the end of this year. Others of you are juniors. You may or may not decide to take calculus here. You may never have to have calculus in your whole life. But in AP Calculus, on the AP exam, all of your decimals must be correct to 3 decimal places. So that is generally, unless I tell you otherwise, what I go by in this class as well. So whenever you're doing any problems, you need to keep at least 3 decimal places for me. If you keep more, it's okay. So like if you had written down for this 1.36521, that's fine, because it's still correct to 3 decimal places. But if you round that to 1.4 or 1.37, I'm not going to like that. That's cut it off too much. So I generally go by that as well. I want everything correct to 3 decimal places at least. There. So unless I tell you otherwise, just get in the habit of keeping at least 3 for that. Here, I could have done this differently. I could have done where I rewrite, where I do log, and my base is 5, and then the 9 goes over here with this, and the x goes over here. But really the only difference there is just the way you're thinking about it, because if you look at what I've got, it's exactly what I had over here. So, you know, either mentality works there. I like the inverse because I think it helps when you get to more difficult problems. So that's what I am typically going to do. So if I look at number 2, I've got 8 to the x power equals 450. So since I have 8 raised to a power, to get rid of that 8 raised to a power, I'm going to do log base 8 on both sides. And the log base 8 will cancel with the 8 that is the base here. And I will just have x. Over here I will have log base 8 of 450. Let's see. Lennon, how do I type that into the calculator? If I'm on this calculator, I can't put the base in, so which one do I put on top? The 450 or the 8? 450. So I'll do log 450 divided by log of 8. And that will give me 2.938 approximately. You'll see that I am putting the squiggly equal sign because I did round this a little bit. That would be preferred. I don't always remember to do that, and I'm not going to count off if you forget to do that whenever you round, but that's why I'm putting the squiggly equal sign. Okay, 3 is a little bit harder. Okay, I need to change 3. No, I don't. No, I don't. It's one of these over here. I don't need to change it. It's one of these over here that's a problem. It's number 5 that's a problem. 5's going to be a problem. We'll see why when we get there. Here, if I want to get rid of that 10 right there, Kendall, what could I do to get rid of that 10? Good. I'll do log base 10 on both sides, which, if you want to write the 10 is fine, but that's our common log, so I don't even have to write the base on this if I don't want to, because it has a base of 10. But if you know, sometimes it helps me to see. There's my base, there's the 10, they match. I cross those out. Now, I actually have more stuff than just the x in my exponent here. So I've got 2x minus 4 equals log base 10 if you want to put it, but you don't have to on this one, of 800. Log of 800 is just a number. We can type that into our calculator. Log 800 is 2.903. So we got 2x minus 4 equals 2.903. There, keep that number in your calculator. You generally don't want to round it till you get to the very end of the problem. If what you write down is rounded, that's fine, but keep it in your calculator. Now I'm just down to like a two-step equation, right? I could give this to my Math 1 kids and they should be able to solve it. So Connor, what would I do to finish solving that equation? Add 4, which is going to give me 2x equals 6.903. And then what would I do after that, Connor? Divide by 2. And here's where you want to make sure you keep it in the calculator because it's going to change it just a little bit. So I'm going to take this number that I had right here. I'm going to add 4 and divide by 2. And I get 3.452. For that problem. So that problem, I had a little bit of work to do after I finished. Number 4, I'm going to have work to do before I am going to use the log here. So for you to be able to use that log to cancel something, you have to have just a number raised to a power, like we had on those first 3. Here I've got e to the x power, but I also got this 10 and this minus over here. I got to clear those out before I can deal with the e. The e has to be by itself raised to a power first. So to get rid of that 10, I would subtract 10. And so don't lose that negative. You got negative e to the x equals negative 19. And the e is still not by itself. I got to get rid of that negative because that's like having a negative 1 out front. So I'm going to divide by negative 1. So e to the x is going to equal 19. And now I just have a number raised to a power because that e is a number, right? So how do I get rid of an e? It is natural log, right? If you want to think of it as log base e, you can, right? Because that's what natural log is, but it's just ln also. Natural logs and e's are inverses of each other. So this will cancel. I'll just have an x over here. That's going to equal natural log of 19. Oops. I'll write that equal sign there. And so natural log of 19 is going to give us 2.944. Okay, questions there? All right, those are solving our exponentials. So to solve exponentials, you should use logs at some point. Let's look at solving logs. To solve logs, we use exponentials. So this log right here doesn't have a base, so what is the base? 10. So if I want to get rid of a log base 10, I'm going to do 10 to that power on both sides. And actually 6 is the one I'm going to have to change. This one is a little crazy. The 10 and the log base 10, they cancel out. I just have the x left. And over here, I'm going to get 10 to the 90th power, which is 10 with 90 zeros. There's 1 with 90 zeros. So we were just going to leave it 10 to the 90th power. On your homework, if you see something like this and you're getting like something to a huge power, just leave it as an exponent. It's okay. Now, example 6, I'm just going to change the problem on this because if you're thinking ahead on number 6, I'm going to end up with 5 to the 20th power, which is going to be gigantic, and then I'm still going to have to do something else. So I'm going to change the problem. Let's just make that a 2 instead of a 20, because otherwise it becomes a really, really difficult, well, not difficult, just really long problem with long, long numbers. So That was my oversight in making the problem. So if I have log base 5 of x minus 4, notice x minus 4 is all in the parentheses, so you're taking log of all of this. How do I get rid of that log base 5? 5 to that power. So 5 raised to the power, 5 raised to the power over here. So that 5 and that log base 5 are going to cancel each other out. I just have x minus 4 on that left-hand side. Over here, I've got 5 squared, which, of course, is just 25. You can see if I had to do 5 to the 20th, it'd be huge. And I'm not done on this one. I need to add that 4 to both sides, so x would equal 29. We're about out of time, but we can get these last two in because they're not too long. You do not divide by 2 first. You got to get rid of that 3 first. Okay, you're going to subtract the 3 first. And so you'll get 2 natural log of x equals 4. And then you will divide by 2. When you're solving equations, opposite of order of operations. So whatever you would do last in order of operations is what you do first when you're solving equations. So natural log of x equals 2. Okay, now I've got it down to where the natural log is by itself. How do I get rid of a natural log? Yeah, the base on a natural log, it's not written, but it is an e. So you're going to do e to that power on both sides. So the natural log and the e cancel out. You just have an x on that left side, and it's going to equal e squared. It feels like e is a variable there, probably especially to you guys because you haven't used e a lot, but it's just a number. And on your calculator, it's second, and the division key will get you e, so you'll do e to the second power. And that's 7.389. So x is about 7.389. And number 8 is one of Coach Wood's favorite problems. What are you going to do on number 8? It's one of his favorite phrases in all of logarithms. If he did not say it to you guys, I'm going to be shocked.
Drop the log.
Drop the logs. He loves to say drop the logs. Sometimes he puts poop emojis next to it as he does these problems. He sent me a text the other day of his screen with poop emojis on it for this. But you are dropping the logarithms, but if you think about what we've been doing, we're also doing the inverse. Because to get rid of a log with a base of 10, you would do 10 to that power on both sides. And since you have a log base 10 on both sides, it cancels on both sides, right? Which just gives you 4x minus 3 equals 3x plus 10. And I'm going to solve this super fast and subtract that 3x because we've got to go. And x minus 3 equals 10. We add the 3. X equals 13. You don't have to necessarily show that, but that's what's happening. All right, so you are going to have homework and a